Hello, Deepak here from Flying 101 and welcome back to another video. I release a weekly video related to aircraft, flying, aviation, and these videos are meant to be quite simple in terms of how the concepts are explained. So if you've ever wondered about things related to flying, planes, etc., click that subscribe button, press that bell notification so you're notified every time a new video is released. In today's video, we'll be exploring something called high lift devices, which are also part of the secondary flight controls. We did a video previously talking about the primary flight controls, but today we'll be exploring something called high lift devices, which are part of the secondary flight controls. Now, before we start talking about the specific devices themselves, let's take a moment to understand the reason for aircraft having these high lift devices in the first place. Why do we have them? Well, quite simply, the reason why we have high lift devices on planes is to reduce their takeoff and landing distances for a given runway length. And this allows planes to carry a greater amount of payload. So we're talking about the passengers, cargo, etc. And it just basically helps planes reduce their speeds whilst takeoff and landings, so they can be accommodated within a given runway length. Having understood that, now let's specifically talk about the actual devices. Let's start off with flaps. So the flaps are the green drawings on the trailing edge of the wing or the rear part of the wing. And what flaps are meant to do is to increase the camber and or the surface area of the wing depending on the design and the type of flap. There are several different types of flaps. We wouldn't actually get into those different types. It's just a high-level overview to give you an understanding of what a flap is and what it does. So a flap basically is a hinged surface to the trailing edge of the wing, which when extended allows the wing, that wing over there, to have a greater camber. So we're talking about the curvature on the top of the wing. If you recall from the video we did on lift happens as a result of a pressure difference between the top and the bottom of the wing. We have a low pressure on the top and high pressure on the bottom of the wing as a result of the air flow over the top flowing at a greater speed due to the camber or this curvature. Now, if this curvature or the camber were to be increased, as depicted in this diagram as a result of the extension of the flap, this would theoretically make the wing generate more lift. Now let's go back to our formula of lift. That's what we have over there. So once again, half multiplied by the density of the air, represented by rho, multiplied by the square of the airspeed, multiplied by CL, which is a coefficient of lift, multiplied by the surface area. Now let's specifically look at the coefficient of lift. If you watched the previous video where we talked about how an airplane stalls, what causes it to stall, CL, or the coefficient of lift, is a function of angle of attack. Angle of attack is nothing but the angle that the wing is making with the relative airflow. So imagine this is a wing and this is a relative airflow. The angle between these two is exactly what the angle of attack is. And this angle, as it's progressively increased, it actually creates more coefficient of lift, which in turn gives us more lift. But this is only possible up to a certain angle of attack, after which a separation of the airflow occurs. If you haven't watched the video on stalls, the previous one that we did, I suggest you watch that because that will give you some more context in terms of how this phenomenon works, what we are exploring over here. So this CL increase is only possible up to a certain angle of attack, after which a separation of the airflow occurs on the top of the wing and it's no longer able to generate lift, and so it loses lift. Now, if it was possible to increase this maximum coefficient of lift as a result of being able to increase the angle, then we could theoretically have more lift, and that's exactly what high lift devices allow us to achieve. So a flap, when extended, gives a greater camber to the wing, or maybe even surface area depending on the design of the flap, and therefore it's possible to achieve a greater coefficient of lift and maybe even more surface area, which makes it possible for a plane to fly at a lower speed to achieve the same amount of lift. Because if we're able to increase these two parameters, it's possible to decrease the speed of the aircraft to give us a given amount of lift that's needed to maintain flight. And that's exactly why we have high lift devices, is to be able to give us an increase in the maximum coefficient of lift and maybe the surface area, and therefore allow us to reduce the speed of the aircraft whilst giving us the same amount of lift. So that's what a flap is. That's an airfoil or a wing with the flap retracted, so it's inward, and that's the wing with the flap extended. So as you can see, it's now got a greater camber and maybe even surface, depending on the design of the flap. But that's basically what it does. Now, in case you're wondering, why don't aircraft just fly with the flaps extended? It's because it does create a lot of drag. Once these surfaces are extended, it creates a lot of drag, and therefore the plane becomes quite inefficient in terms of its fuel consumption and performance. And so these are only employed typically whilst takeoff and landing. Once a plane has taken off and it's reached a certain speed, the flaps will be retracted. For any of you who have been frequent flyers, and if you've sat over the wings, you may have noticed during a takeoff or just before the landing that these surfaces on the trailing edge of the wing would tend to slide out. So, having looked at flaps, now let's understand what slats are. Slats are high lift devices again, and they are typically on the leading edge of wings. We're talking about the front of the wings, as represented by the drawings over here. Slats, once extended, so that's an extended slat over there, allow the boundary layer over the wing to be re-energized. All right, let's break that down simply. So remember, once again, when an airfoil or a wing is generating lift, we've got high pressure at the bottom and low pressure at the top. There's a pressure difference, and that's what's giving us lift. Now, if it was possible for us to have some of this high pressure air flow over to the top, because remember, air always flows from high pressure to low pressure. That's how it works. If this air from the high pressure region was able to flow to the top, where we have relatively low pressure, that would actually give us more kinetic energy. So as the airflow is happening at the top, with the increase in the angle of attack, or the angle between the wing and the relative airflow, it gets to a point where, again, we're going back to our coefficient of lift over here, it gets to a point where it can only reach a certain angle after which a separation of the airflow occurs. And so the plane or the wing is no longer able to generate lift. However, if we had a slat extended, it could help with some of this high pressure air flowing over to the top to re-energize that boundary layer. So when we're talking about a smooth airflow over the wing, in normal conditions, we've got a smooth laminar airflow, therefore we have a boundary layer. It's like there's viscosity between the airflow and the wing, and that's giving us a pressure drop on top, and so lift is created. But yes, so if we didn't have the slats extended, and if we continue increasing the angle of attack, so the angle between the wing and the relative airflow, it would only be possible up to a certain angle after which a separation of the airflow would occur, and so the wing will no longer be able to generate lift. Now, if we had the slat extended, and if we could use some of that high pressure air at the bottom to flow through the slot to the top of the wing where we have the relatively low pressure, because remember, air always flows from high pressure to low pressure, this could actually add more kinetic energy to the airflow that's on top of the wing, and so it would re-energize the boundary layer. And with this re-energization of the boundary layer, lift can be sustained even at a greater angle of attack. And so, once again, it would be possible to generate more coefficient of lift and therefore reduce the airspeed, because if one of these can be increased, the speed of the aircraft can be decreased to generate the same amount of lift. And that's exactly what a slat does. So once again, a quick recap. slats are typically on the leading edge of the wings, and once extended in flight during takeoffs and landings, they allow for the boundary layer, so the airflow over the top that's happening smoothly, to be re-energized at a higher angle of attack, so the angle between the wing and the relative airflow. Flaps, which are typically found on the trailing edge, there are some aircraft which have flaps on the leading edge as well, but for the purposes of this explanation, let's just consider flaps to be on the trailing edge. They would allow for the camber of the wing to be increased once extended, and maybe the surface area too, which will allow for a greater coefficient of lift and surface area, and so it would be possible to reduce the airspeed to generate the same amount of lift and therefore reduce the takeoff and landing distances. Alright, so there we have it, our high-level and simplified explanation of what high-level devices are. Once again, I sincerely hope that wasn't too difficult to follow, it wasn't too technical, and it made some sense. As always, if you've got any comments or if you have any questions, please pop them below and I'll do my best to answer them. Alright, so thanks very much once again for your time, and I look forward to seeing you next week. Thanks and have a great day.